This is an animated tutorial on how to solve various types of stoichiometry problems. We will first look at simple problems involving moles, then mass. Then we will look at how to determine the percent yield of a given product. Finally, we will solve a problem in which we must first determine the limiting reactant before figuring out how much product is produced. Stoichiometry is the study of quantitative relationships found in a balanced chemical equation. In other words, it's an approach to problem solving in chemistry using a chemical equation. We'll be using BCA tables, or before, change, after tables in stoichiometry problems. These tables allow us to track quantitative changes in a chemical reaction, such as how much product can be or should be produced, how much reactant will be consumed in the process, and how much, if anything, is left over. Before beginning, let's review what a balanced chemical equation shows us. Here is an equation for the formation of water from two different gases, hydrogen and oxygen. The coefficients in front of the formulas tell us how many particles of each substance react and form. For example, according to our equation, 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to form 2 molecules of water. The coefficients also tell us how many moles of each substance react. In other words, the coefficients also express mole relationships in addition to particle relationships. If you remember from our mole unit, we define a mole as a unit of measurement for dealing with extremely large numbers of very tiny objects, such as atoms, molecules, formula units, and ions. 1 mole of anything, whether it's oxygen gas, or perhaps smiley faces or bikes, contains 6.02 times 10 to the 23 of that thing. So the number of moles and the number of particles both describe quantities that can be counted. In other words, they both describe how many of each substance we are working with. Now that we have established the basics, let's see an example of how to solve a basic stoichiometry problem. Let's look at sample problem number 1. Hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. How many moles of oxygen gas will be needed to completely burn 8 moles of hydrogen sulfide? To start off this problem, we're going to write the balanced chemical equation to describe the reaction and its mole ratios. According to the balanced equation, the coefficients should read 2, 3, 2, and 2. Now we will set up our BCA table, where B stands for before, C stands for change, A stands for after. We're going to fill in the before line with a number of moles of starting reactants. We will write 8 moles for hydrogen sulfide, since this is given in the problem. You can assume that the reactants you don't have specific amounts for are present with more than enough available. In this particular problem, there is no mention of the amount of oxygen gas. For such a substance, we will write XS to show that it is in excess and will not run out. Since the reaction has not started, there are no products, so we will write 0 moles for both sulfur dioxide and water. Now we will determine what information we are trying to find, in this case the number of moles of oxygen gas needed to completely react with hydrogen sulfide. In our BCA table, it is the box with a change in oxygen in the reaction. We're going to now fill in the change row, which will indicate how much the amount of reactants and products changes over the course of the reaction. Remember, the reactants are always consumed, so we will show this with a negative sign, and products are always produced, so we will show this with a positive sign. Next, determine which reactant is completely consumed. In this case, hydrogen sulfide, since it is stated in the problem. To determine how much of each of the other substances changes by, we will use the mole ratios found in our chemical equation. The mole ratio, remember, is also the coefficient ratio. For example, according to the equation, for every 2 moles of hydrogen sulfide, 3 moles of oxygen is required. Hopefully this statement sounds familiar. These are the for every statements that express quantitative relationships, and we call these proportional reasoning statements. Since 8 moles of hydrogen sulfide are used up, we will consume 12 moles of oxygen gas. We'll get this number, 12, from multiplying 8 moles by our mole ratio, or the proportion, which is 3 to 2. Finally, we will use the mole ratios between the reactant that is completely used up and each product to determine how many moles of each product is formed. The mole ratio between sulfur dioxide and hydrogen sulfide is 2 to 2. Therefore, if 8 moles of hydrogen sulfide are used up, 8 moles of sulfur dioxide will also be produced. This is the same for water, since it is also related to hydrogen sulfide by the same mole ratio. Finally, we will complete the table with what remains after the reaction is complete. The after line is simply the sum of the previous two lines. Adding together the before and change rows, we get 0 moles of hydrogen sulfide, an excess of oxygen gas, 8 moles of sulfur dioxide, and 8 moles of water. So, according to the BCA table, 8 moles of each product will be formed, hydrogen sulfide will completely be used up, and 12 moles of oxygen gas will be consumed, but there will still be an excess of it at the end. It is important to remember that only moles go in the BCA table, never mass, because the balance equation deals with how many particles, or mole relationships, and not how much, which describe mass relationships. Let's try another slightly more advanced stoichiometry problem involving starting masses and percent yield. Suppose 4.61 grams of zinc was allowed to react with hydrochloric acid to produce zinc chloride and hydrogen gas. How much zinc chloride should you get? We will start again by writing the balanced chemical equation to describe the scenario. Then we will set up our BCA table and fill in the known information. Since the problem gives us mass data, we cannot use information directly in our BCA table. Mass data tells us how much of substances we have without telling us how many particles are available to react, so we must first convert the mass of the reactant into moles. Dividing zinc's mass by its molar mass of 65.39 grams per mole, we get 0.0705 moles. Note that there is no specific amount of hydrochloric acid given. We can therefore assume that it is in excess. And since the reaction hasn't started yet, there are 0 moles of products. Let's revisit what the problem is asking for. How much zinc chloride should you get? This is a clue for finding the theoretical yield, which we can obtain directly from our BCA table. The amount of product formed depends on the amount of zinc we start with. And according to the balanced equation, the mole ratio of zinc chloride to zinc is 1:1. So for every 1 mole of zinc consumed, 1 mole of zinc chloride will be produced. And since 0.0705 moles of zinc will be used up, 0.0705 moles of product will also be formed. But we are not done yet. The problem asks for how much product, not how many moles of product. So we need to convert moles of zinc chloride into grams of zinc chloride. The molar mass is 136.29 grams per mole. Using this information, we get 9.61 grams of zinc chloride. Now suppose that in the experiment we actually recovered 8.56 grams of zinc chloride, which happens to be less than the predicted amount. Our reaction was therefore not perfect. In order to objectively evaluate the success and efficiency of our reaction, we will perform a percent yield calculation in which we compare the actual yield, or experimental yield, with a theoretical yield. Here is the formula. For this particular problem, our percent yield is 8.56 grams divided by 9.61 grams times 100%, or 89.1%. Let's look at a third sample problem, which is a limiting reactant problem. When 13.5 grams of aluminum reacts with 183 grams of iodine to form aluminum iodide, how many moles of the excess reactant will remain, and how many moles of aluminum iodide will be formed? The first step to determining the limiting reactant is to find out how the two reactants interact quantitatively. We do so with the coefficients, which we get from a balanced chemical equation. So the first step to problem solving remains the same. Write the equation. Next, we need to convert our given mass values into mole values so that we can make use of the mole relationships expressed in our equation. Aluminum has a molar mass of 26.98 grams per mole, and iodine, in its natural diatomic state, has a molar mass of 253.8 grams per mole. 13.5 grams of aluminum is equivalent to 0.5 moles of aluminum, and 183 grams of iodine is equivalent to 0.721 moles of iodine. Our balance equation tells us that 2 moles of aluminum will react completely with 3 moles of iodine to form 2 moles of aluminum iodide. Therefore, we need 3/2, or 1.5 times as many moles of iodine as aluminum. Do we have enough? Which reactant runs out first? To see which reactant gets consumed completely, we will use mole ratios with the starting number of moles to figure out how much of each reactant would be needed. For example, To completely consume aluminum, we would need more iodine, specifically 3/2 more, where 3/2, or 3/2, is the proportion. This gives us 0.75 moles of iodine. Unfortunately, we only start with 0.721 moles, so we do not have enough. Iodine will run out before aluminum is completely used up. Let's confirm that iodine is indeed the limiting reactant by figuring out how much aluminum is needed to completely react with 0.721 moles of iodine. Since the mole ratio between aluminum and iodine is 2 to 3, we need fewer moles of aluminum. 0.721 moles times the proportion 2/3 gives us 0.481 moles, which we certainly have. Therefore, we will have aluminum remaining after iodine is completely consumed. In other words, aluminum is the excess reactant and iodine is in fact a limiting reactant because it runs out first. Now that we have determined which reactant is limiting, we can determine the theoretical yield of our product. The number of moles of aluminum iodide that can be formed will be limited by the starting number of moles of iodine, the limiting reactant. According to the coefficients in our equation, 2 moles of product will be formed for every 3 moles of iodine. Aluminum iodide and iodine are related by a 2 to 3 mole ratio. Therefore, the change for our product will be 0.721 moles times 2/3, or 0.481 moles. At the end of the reaction, we will have 0.019 moles of aluminum left over, no iodine remaining, and 0.481 moles of aluminum iodide produced. If we want to figure out how much in grams aluminum iodide is actually produced, we can multiply the number of moles by the molar mass of aluminum iodide, and this will give us 196 grams. Likewise, if we are interested in the mass of aluminum left over, we can multiply 0.019 moles by aluminum's molar mass, and this will give us 0.513 grams. So we started the reaction with 196.5 grams in our system, and we ended the reaction with 196.5 grams in our system. The total mass of the system is conserved in a chemical reaction. No matter is created and no matter is destroyed. Rather, the atoms involved in the reaction are simply rearranged to form a new compound. Notice how the total number of moles of chemicals in the system is not conserved. We started off with about 1.22 moles of reactants, and we ended with 0.5 moles in our system. This tells us that while the total number of atoms is conserved, the total number of particles, which includes molecules and formula units, does not necessarily have to be conserved. We can see this also looking at the coefficients in our balance equation. 2 plus 3 does not equal 2. So in summary, you have just seen 3 examples of stoichiometry problems in order of increasing difficulty. All types of stoichiometry problems can be approached with a BCA table. Remember that only moles or number of particles go into the table, not mass data. Remember that how a reactant or product changes is based on mole relationships determined by a balanced chemical equation. So the first step is always to write a balanced equation. Remember that the BCA table gives you the theoretical yield of a product, not the actual yield. To determine the percent yield, you will divide the actual yield by the theoretical yield and multiply the result by 100%. And unless matter is added to the system or leaves the system unintentionally, the percent yield should be 100% in accordance to the law of conservation of mass.